Welcome to our first video in the solution chemistry series. In this video, we're going to be looking at the different components of solutions and examining a variety of materials that are actually solutions, even if you didn't think they were. We start, however, with the simplest and most common solution, salt water. Not surprisingly, one of the components of salt water is salt. Salt, NaCl, is what we call the solute, which is the substance that is dissolved into and by the other compound. Water is the second part of salt water, which is what we call the solvent. And the solvent is the substance that does the dissolving of the solute. In other words, salt, the solute, dissolves into water, the solvent. Try saying that 10 times fast. So when water causes NaCl to dissolve, you can tell that salt has completely dissolved because the NaCl will no longer be visible within water. We cannot tell where the water ends and where the salt begins because the salt has disappeared into the water. When this has happened, you have just successfully made a solution. But what about substances like sand that do not dissolve in water? No matter how much water you have, and no matter how much you shake this beaker, can you get the sand to completely dissolve in water? For anyone who's tried this, the answer is obviously no. Since we cannot get the sand to dissolve, basically at all, sand in water is not an example of a solution, but is an example of what we call a mechanical mixture. One way to classify mechanical mixtures versus a solution is to talk about something that we call phases. Another word for phase is the more common word layer. Now we can see that a mechanical mixture of sand and water has two visible layers. There is the solid layer made of sand and the liquid layer made of water. For this reason, because we can obviously see that sand and water are different, the other word that we use to describe mechanical mixtures is the word heterogenous, where hetero is the Greek prefix that means different. For a more extreme example of layers, if we take a look at this three-phase mixture, we can see the oil layer floating on top of the water layer, and which in turn is on top of the sand layer. Now, is it possible to tell where the oil layer ends and where the water layer begins? Well, obviously the answer is yes, because we can clearly observe this. Therefore, because we see three different layers, this mixture is what we call heterogeneous. However, if we were to look at a saltwater solution, is it possible for us to see where the water ends and where the salt begins once the salt is dissolved? Well, the obvious answer is no, and if you can claim to see NaCl ions floating around in here, please tell me how you did that. Since we only see one visible phase here, this is not a heterogeneous mixture because we cannot see two different compounds within here. And as a result, because it all looks the same, we can call this mixture homogenous, where homo, of course, is the Greek prefix that means same. Next, we can take a look at a variety of different solutions to see how much diversity within the definition of solution we can get. If we think about solids that dissolve into water, salt is probably the first one most people think of, but sugar is followed closely behind. Now, we know that we can dissolve both sugar and salt in liquid water. Again, dissolving substances in ice doesn't really work very well. But because sugar and salt are both solids dissolved in liquid water, this is, unsurprisingly, what we call a solid-liquid solution. Now, is it possible to have a liquid-liquid solution? Actually, they're more common than you think. For people that know the chemical components of beverages purchased at your local LCBO or at the beer store, they will know that ethanol, which most people commonly know as alcohol, is actually a liquid. So both water and ethanol are liquids, and the irritating thing is that both of them are colorless. So generally, we're pouring one colorless liquid into another colorless liquid, and once again, if we look, can you see where the water ends and where the alcohol begins? I cannot. Therefore, since this is only one phase, and since ethanol and water are both liquids, this is what we call a liquid solution. That means that any of the alcohols that you know about, beer, wine, vodka, baijiu, or whatever, are all examples of liquid solutions. What about the air that you breathe? Everybody knows that the main gas that we need in the air is oxygen. But is oxygen the only gas in the air? Obviously, the answer is no. In fact, oxygen is not even the most common gas that we have in the atmosphere. That belongs to nitrogen. So if we ask the one phase or more than one phase question about Earth's air, can you see which part of the air is oxygen, which part of the air is nitrogen, which part of the air is CO2? I personally can't, but if you can, please feel free to tell me how to recognize which atom is oxygen and which atom is nitrogen. So here, because air is actually a mixture of different gases, and since we can't tell where one gas layer begins and the other gas layer ends, we can consider air to be a gas solution, a mixture of certain gases that are effectively dissolved by more numerous gases. Now, getting close to a topic that is near and dear to my heart, hence the French horn here, if we consider these two metals here, the French horn is an example of a brass instrument named after the type of metal out of which it's made, and these coils here are examples of the most common alloy on Earth, steel. As mentioned by what I just said earlier, steel and brass are what we call alloys, which are actually mixtures of multiple metals. So, for example, steel is a mixture of iron, and usually, in order to give it the high resistance to bending, it's got carbon mixed in with it, whereas brass is a mixture of copper and usually other elements such as zinc. Other times there's chromium in there, and so on. Now, if we look at each of these metals here, can you tell in brass where the copper ends and where the zinc begins? Likewise, can you see individual carbon layers within the steel? Once again, I cannot. Because of this, because these metals are effectively mixtures of more than one metal where we cannot see the individual metals within, these are technically solid solutions. Again, we don't normally think of solids as solutions, but following our definition, they technically are. As a little bit of a trick, if we consider milk, we know that milk is a mixture of many different substances, most notably water and the fat that is actually the solid white particles that give milk its characteristic white color. Now, normally, if we look at milk like this, we would expect that milk would be a solution because we only see one phase. However, appearances can be a little bit deceiving. If you leave milk on the counter for a week or longer, I would highly recommend against this. You can see, as a result of leaving this jar of milk for a while, that the water and the fat actually separate from each other, causing it to form two different phases, because as we know, oil and fat does not dissolve in water completely. Milk is a weird example in that it can form one visible phase, but will separate given enough time. And for that, we call it a special mixture that we call a colloid, which again is a mixture of two different substances where they're effectively forced to be together, but will separate if given enough time. Under a microscope, it is painfully obvious that water and fat particles do not actually mix, because we can see the individual fat particles forming spheres like this, and the space in between is the water, showing that the compounds clearly don't match. In the next video, we're going to look at one of the different types of reactions that is used in order to form some of the more common solutions that exist in our day-to-day lives.